Hello, everyone. Thank you for joining us today. My name is Adrian, and I'm a Director of European Workflows at Unchained Labs, and I'll be your moderator today. I'm very glad you've decided to spend part of your day with us. Before we get the seminar started, I wanted to remind any customers joining us today that Unchained Labs is dedicated to supporting you through this challenging time. Please do not hesitate to get in touch with your local sales specialist, application scientist, service engineer, or reach out to us directly at our website if you need anything. We're ready to do everything we can to help you. We'll have a question and answer session at the end of today's presentation, and to ask questions, all you have to do is click on the question and answer in the Zoom navigation bar at the top or the bottom of the screen and type in your question, and we'll get to as many of those as we can. And now I'd like to introduce Joe Barco. Joe is our Senior Director of Workflows Marketing. And today, Joe will be taking us through how Big Tuna can be used to automate buffer exchange and sample prep. And now I'll hand it over to Joe.
Thank you, Adrian. Good morning, everyone. Thank you for joining us today as we talk about how to automate buffer exchange and simplify sample prep with Big Tuna. If you're joining me this morning, I'm going to guess it's because you do protein buffer exchange, and you want to see if Big Tuna can help make that process better. You probably also never thought that you would spend any time thinking about buffer exchange. It's a simple process of moving protein from one buffer into another. It's a chore. It's a task, like folding laundry, just something you have to do to get on with your day and to get to something else. It is a task that shows up everywhere. It's ubiquitous. Anytime we're doing protein characterization, protein purification work, it involves some level of transferring buffer, concentrating protein, moving it into some other desalting step. All of it is some form of buffer exchange. Any type of drug developability we're doing, so formulation, screening, optimization, labeling proteins such as ADC or biotinylation, some level of purification that's essentially a buffer exchange step. If we take a step back and look at the biologics drug development process, we're always looking for approaches that accelerate the development of a drug without sacrificing quality. It's difficult to be the person that says there's not enough time or not enough material to do one more characterization test, or to study that anomalous result, or figure out just how stable that drug is in that formulation. Automating buffer exchange actually makes sense here. Higher throughput applications generally drive doing more with less, as you can run on a lower scale. It also minimizes the labor burden on buffer exchange and increases the time to spend doing more science. Buffer exchange needs vary widely through the development process. Earlier stages may have more candidates at lower concentrations, while later stages are generally one or a handful of candidates, usually at very high concentrations. So bringing automation to the buffer exchange process should address both of these areas to be an effective solution. Now, despite buffer exchange showing up everywhere in the drug discovery process, the processes are still fairly manual and low-tech. Dialysis, you accept that you're going to run overnight, that you're not going to get your protein until the next morning, and it's going to be more dilute than when you started. For centrifugal filters, you accept that you're going to spend the whole day at the centrifuge, running back and forth every 15 or 20 minutes, hoping that every well is running the same, hoping that there's not a membrane clogging, hoping there's not some solution that's just not running as fast as everything else. For TFF, you're further along, and you're going to start at 100 mils. So as long as you have 100 mils of protein, as long as you're willing to commit to half a day to a day of setting up the pumps to get it to run right, and as long as you accept that cost of that consumable, you're fine. At this point, I'd like to introduce you to Big Tuna. Unchained Labs developed Big Tuna to be a fully automated walk-away buffer exchange system. It is designed to be simple to set up and use. Within 30 minutes, you can design an experiment, set up the deck, and walk away, even if you've never used automation before. Big Tuna can handle sample volumes as low as 100 microliters per well, up to 8 mils per well. You can exchange or concentrate up to 96 samples in a single run, and that could be as simple as one protein into one buffer or 96 different proteins into 96 different buffers. Big Tuna can handle protein concentrations in the sub-milligram per mil range all the way up to 200 mg per mil. Well, Big Tuna uses filtration plate-based buffer exchange. We developed these plates called the unfilters to accomplish this work. So we have unfilters in a 96 well format that handles the lower protein volumes, so 100 to 450 microliters. We have those in a number of different molecular weight cutoffs between 3 and 100 kilodaltons. The unfiltered 24 handles the higher end of the range, which is 0.45 to 8 mils per well at a 10 kDa cutoff. Both of those are regenerated cellulose. The price per well is comparable or less than what you have in dialysis or centrifugal filters. There are many drivers to automate a manual process. One of those drivers could be to increase sample throughput. If I look at my unfiltered 96 data, shown here in the green columns, I see that I can complete up to 96 exchanges at the same time in as little as an hour. Generally, protein concentration increasing will increase the sample viscosity, but even at 50 mg per mil, I can fully exchange 96 proteins at the same time in under 3 hours. Another driver for automating a process is to increase walkaway time. If I look at my unfiltered 24 data, shown here in the blue columns, I can still complete 24 exchanges simultaneously in about an hour. At higher protein concentrations, such as 50 mg per mil, that exchange is going to take 6 hours. Now that's 6 hours I get back that I'm free to do anything else besides stand in front of a centrifuge and check buffer volumes. Another driver to automate a manual process is to improve the consistency and quality of the final product. Here, Big Tuna has some capabilities that are just not possible with manual buffer exchange methods. These capabilities give you as the end user total control about how buffer exchange works for your particular experiment, even when you've walked away from the instrument. I've highlighted a couple of those features here. One of those is the percent removal, which is the amount of buffer that gets removed in each exchange cycle. Why is this an important feature? Well, let's say you have a protein that is prone to aggregation, that you don't want to overconcentrate. Here you can set a low percent removal, which ensures that you slowly remove buffer and replace it without ever overconcentrating the well and risking aggregation. The opposite end, if you have a very dilute protein, what you have the capability to do is set a high percent removal so that you exchange the new buffer in faster. Percent exchange is the amount of total buffer replaced. The minimum threshold for that is 96% exchange, which is the 96% of the new buffer replacing the old buffer. For more stringent conditions, you can run that up to 99% exchange. And then you have the capability to set a final concentration that's different than what your initial concentration was. So what you can do is you can run, say, 8 mils of a protein, concentrate it down by up to 16-fold, so up to 450 microliters in the final volume. What this does is it gives you a flexibility of not having to do dialysis and then follow it up with centrifugation to hit a specific concentration target. Big Tuna does it all in a single run. The concentration targets were usually within 10% of the target for each protein, even if you have different conditions running in the same plate at the same time. The overall process runs similarly to how you would run a centrifugation filter. You have your input sample. You've input in Big Tuna the set volume you want to remove per cycle. It pressurizes in the chamber to hit that target and then automatically refills with the new buffer. It repeats that process automatically until it's exchanged into the new buffer. You also have the option to concentrate into a new volume at the end of it. If your protein's already in the buffer that you want, you could just concentrate that down. And so you input a target volume that you want, and then Big Tuna will just concentrate down to that specific volume. We designed the software to be fairly simple and straightforward, the intent being that people who are not comfortable with automation could still walk up to Big Tuna and figure out how to use it even on the first try. So what we do is we have a wizard-based system with the chevron set up that step by step the operator enters what they're going to run. They enter where their proteins are going to go, what buffers they want to exchange into. Big Tuna will figure out how your deck should be laid out, how much buffer you're probably going to need to complete the exchange, and tell you where to put everything on the deck. At that point, you hit go, you walk away. If you're ever curious while it's running as to how close you are to completing it, you can look across the room and see the status bar showing up about where everything is at and get an idea about how the plate is running. If your protocols run consistently from run to run, you can save the experiment, so the next time you just tell it what proteins you want to go and where things are at, and then you can just run even faster the next time. So here's what happens on Big Tuna after you hit start. First thing it does is it measures the volume in each well. It does this with an acoustic non-contact sensor. Then what happens is the plate gets pressurized to about 60 psi or 4.1 bar, usually with CDA or nitrogen. It's pressurized while it's gently orbitally mixed for a few minutes. Then pressurization stops. Big Tuna measures the volume again to determine how much volume has been removed by that process. Then each well is refilled to the initial target with a new buffer. This process repeats, pressurization, measuring volume, refill, until each well has reached the exchange sample target. We're often asked, why are you mixing while you're doing your pressurization cycle? Really, it comes down to Big Tuna works by a modified UFDF process. On the left is a diagram of dead-end ultrafiltration, which is similar to how a centrifugal filter runs. Now what happens is everything gets concentrated at the membrane site. This could potentially lead to membrane fouling. It could potentially lead to protein aggregating. And also flow ends up slower because of the concentration of material at the membrane surface. Orbital mixing gives it more of a TFF feel, where nothing is really concentrating at the membrane. That allows flow to occur faster, and it reduces the likelihood of protein aggregating or fouling the membrane. So ultimately what Big Tuna does is it takes one of your chores off your hands, and so then you can focus on doing other things while your buffer exchange is happening. I'm going to walk through a few case studies. I'm going to start with protein purification. The likelihood of protein purification is I have a lot of proteins at low volumes, and so what I'm going to try to do is concentrate protein using Big Tuna into a more reasonable protein concentration. So during the early development stage, the expressed proteins usually come in very diluted after purification. And so to get to a practical volume, a practical concentration for a functional assay, or even just for storage, we have to reduce the sample volume down. With current methods, there could be multiple steps of collecting filtrate, collecting fractions, pooling those fractions, and then doing something like a spin filtration method to reduce the volume. Since we're still in early development, we probably are doing this with a lot of candidates at the same time. In this example, we'll use Big Tuna to completely automate the concentration of these 3 diluted monoclonal antibodies. We'll start from about 350 mils of 0.1 mg per mil concentration for each antibody. We'll distribute the antibody into 6 wells of an unfiltered 24. We'll pressurize to remove filtrate. We'll add back 4 mils of the diluted antibody into each well after each filtration cycle. So think of the dilute antibody as the new buffer from my description earlier. We estimated we can completely reduce 350 mil volume in about 15 cycles through this process. The successful experiment will show that about 50-fold concentration from 350 mils to 7.2 mils, and then sample concentration increasing from 0.1 mg per mil to 5 mg per mil. So Big Tuna was able to achieve over 60-fold concentration for the 3 antibodies in a single automated run. So for each antibody, we were able to reduce the volume from approximately 350 mils down to a final volume between 6 and 8 mils. This method's concentration is fully automated, so you just need to set up Big Tuna, come back to the finished sample, ready for downstream analytics. It's especially beneficial when you have to juggle between a lot of different proteins. So now you can finish them in parallel with a consistent final volume and ready to go on to the next step of the process. So now that we have protein in a working concentration and volume, we may want to do buffer exchange to concentrate further for long-term stability or to start doing formulation testing. So this level of sample preparation will get the sample ready for further testing. Unfortunately, the standard processes to prepare protein samples for further testing can be laborious. In development programs, samples usually have to go through dialysis to exchange into the correct buffer. Usually this is a day lost. Then the samples are manually transferred into a centrifugal filter to further concentrate the sample to the right working range. This is a tedious step, especially if you have many protein samples to process through. You have to track each sample in the rotor, eyeball the volume removed after each cycle to get everything to a uniform concentration. While some samples might get to the target concentration quickly, some may take a while depending on the concentration and viscosity that you're working at. And besides tediously checking it, if you don't pay attention, you have to worry about some samples over-concentrating during the process. It sure would be nice to automate this and hopefully do it in a faster and more consistent manner. In this example here, we're going to exchange 3 monoclonal antibodies that we concentrated from the previous experiment. So we'll take 6.5 mils of the 7 mg per mil antibodies and start by first buffer exchanging them into a new formulation. And then we'll concentrate down the sample even further to 100 mg per mil. For the buffer exchange part, in the Big Tuna software, we'll set the exchange parameters to 50% removal for each filtration cycle, and we'll target the new formulation replacement to 96% exchange. After the formulation is exchanged, we'll then have Big Tuna concentrate the sample down 14-fold to try to achieve 100 mg per mil concentration for each antibody. The buffer exchange and concentration steps are all done in a single run. There's no need to transfer the sample out of the filtration plate required. Overall, the buffer exchange step for this took about 4 hours, and the concentration step took an additional 2 hours. Big Tuna was very much on point with this run. We were able to exchange 3 different proteins into 3 different formulations and then concentrate each sample to over 100 mg per mil. Each sample had very high recovery, even at that concentration of over 94%. So we can easily get our protein samples into the right concentrations and volume ranges suitable for any downstream application. We'll do that without making buckets of buffer or watching a centrifuge all day. One more thing I want to point out here, these samples came from the previous concentration run example, so the very dilute antibody that started at 0.1 mg per mil. So we were able to first concentrate that 60-fold there, and then an additional 14-fold here. So overall, Big Tuna concentrated my protein down by about 1,000-fold without having to go through dialysis, centrifugation, TFF, or precipitation method. Now I'd like to transition into Big Tuna for protein characterization prep as a proof of concept. Now, analytical instrumentation is obviously important for protein characterization, but if it requires a specific buffer or a specific protein concentration range to operate, no matter how powerful that instrument is and how useful that data is, you're still going to have a bottleneck at buffer exchange. So what we think is Big Tuna can help you get to those analytical measurements faster and help you scale as your needs for sample throughput increases on the analytical measurement as well. In this example, we'll just highlight a high throughput way to prepare 96 samples for an LC mass spec run. So we'll start with a monoclonal antibody set that's in a phosphate-based buffer with high salt concentration. For mass spec, we want to remove the salt. We also want to put in a slight amount of methanol and a little bit of formic acid to aid in ionization. So because this is a simple buffer we're transferring into and we just want to desalt, we really want to quickly do the buffer exchange and get into the analytical measurement. As you can see here, Big Tuna did the desalting and exchange of 96 samples in less than 2.5 hours. So the final volumes and concentrations were precise, so we see the whole plate is exchanged uniformly. Of course, you could do this prep with other 96-fold plate methods such as a vacuum filter or centrifugation, but those methods do suffer from edge effects, and that ultimately would have skewed results or led to an additional step to have all the sample volumes and concentrations consistent. So by doing the exchange consistently and uniformly, you can more efficiently move into the analytical measurement faster. Okay, my last example, I'm going to talk about developability and formulation work. So I'm going to do some combination of formulation screening and optimization, and I'm going to, of course, use Big Tuna for that. The intent behind formulation screening is to take your drug, which you already know is potent, and determine a buffering condition that is going to confer stability, aid in a longer-term shelf life, all without causing aggregation, and also while allowing the biologic to retain potency. It's not only important to identify a good formulation, but it's important to characterize the protein as effectively as possible because it's expensive to determine a year or two into a shelf life study that you picked a bad formulation. So there's a lot of characterization studies that need to occur during this process. And the more information early on, the better the risk is mitigated. So part of this mitigation risk is to characterize behavior at higher concentrations, since the drug will likely go through high concentration stages, if not at the final injectable level, but almost certainly during the manufacturing process. For formulation screening, many companies will work with platform buffers, for example, 24 different buffers that historically are the same or close to existing buffering conditions. And for formulation optimization, it might involve small tweaks to the best identified condition in order to explore the robustness of the chosen condition. So this could be small variations in pH or the testing of the excipients. So no matter what way you slice it, there's a ton of buffer exchange that has to happen to have this process work effectively. Here's an example of how Big Tuna can really help in formulation development. In this experiment, we loaded 4 different monoclonal antibodies with starting concentrations of 10 mg per ml in an unfiltered 24. We exchanged 6 different excipients into each antibody first, and then we concentrated the antibodies down to its new formulation by 5-fold to reach a 50 mg per ml final concentration. So we wanted to see what the best excipient would be for each antibody at the end of the experiment. We started with 8 mils of an initial volume in each well, set Big Tuna exchange parameters to 66% removal each cycle, and then exchange is complete at 96% exchange. Going ahead to the final exchange result, we're able to buffer exchange 24 unique samples in about 7 hours, and then concentrate those samples 5-fold in an additional hour and a half. This experiment, Big Tuna handled buffer exchange of 4 different antibodies with 6 different formulations, fully automated in the same run. From the data in the table, we see the final concentration for each well. Big Tuna completed the exchange consistently with concentrations at about 50 mg per ml. The next step that formulation scientists may do is to start characterizing the antibody in the new formulation buffer. Here we're going to use another of our analytical instruments, the UNCLE, to start this characterization by monitoring thermal stability. So we get a lot of data from this measurement. There's usually multiple thermal melting transitions for each antibody, but not to belabor this, I'm going to focus on only one antibody, which is MAB4, and the first thermal melting transition. So compared with our no excipient control, which has a thermal melting at 70.5 C, we can see that we have 3 excipients that increase the thermal melting stability, which are sucrose, mannitol, and glycine. So it seems like right away we've identified a lot of conditions that can help increase the TM. We don't need a lot of protein for this measurement, only 9 microliters, so there's plenty of other antibody in this formulation that we have left over to do some of the many other analytical measurement techniques that usually need to happen to determine the best formulation candidate. Now, if I were standing in front of you in a conference room, this would be about the point where you would ask me, how does Big Tuna handle proteins running at different rates? So that's a very fair question to ask at this point. So the flow rate is going to be dependent on the biophysical characteristics of the protein, and it varies across the protein concentration, and it's hard to predict ahead of time. And it's especially not worth the trouble of figuring it out when you're just screening and you haven't really even committed to a formulation yet. So while Big Tuna can't alter the biophysical characteristics of your protein, it can measure what's happening and compensate for variations in flow. So remember, Big Tuna is measuring the volume at every time the pressurization stops. So it knows right away if one well or a set of wells is running differently than others. So it uses the volume measurements before and after the pressurization cycle to calculate a flow rate for each well. In this particular experiment, MAB3 was running faster, about twice as fast as MAB2. Why? It's not really important right now, right? It's just what to do about it. And Big Tuna knows that the parameters that you entered, and the parameters are not to do more than 50% removal per cycle. So the process the rest of the way will ensure that MAB3, which is running really fast comparatively, doesn't go past that 50% removal target. Overall, that means the whole plate might take a little bit longer to complete, as we still have to meet the overall percent removal target. But at the end of the day, it means that everything is exchanged consistently with less risk of something going wrong during the exchange process. So Big Tuna tracks this flow rate throughout the exchange process, which makes sense as you'd expect flow properties to vary as you're in the process of changing buffers and your intermediate concentrations. So we can take this information and plot it, and you can see pretty quickly how the flow rate varies between antibodies and between excipients. So for example, if you look at the contrast between MAB2 and MAB3, at that first measurement, MAB3 is already far to the right, suggesting that a greater percent exchange at the outset. You can also see in some antibodies, the excipients have little impact to the flow rate, such as on MAB2 and MAB1, while in other antibodies, such as MAB4, there's a wide discrepancy and disparity between how excipients impact the flow rate. Let's focus on the MAB4 flow rate plot, and let's recall the excipients that conferred extra stability were mannitol, glycine, and sucrose. Compared to my initial buffer condition, everything had an improved flow rate. But there's a variation by a factor of 2, as mannitol, glycine, and the no excipient condition all had faster flow than the other buffers. So flow rate matters. It's going to give me insight into how I expect a high concentration protein to run. Even at this lower protein concentration of 10 mg per ml, sucrose is having a negative effect and reducing flow rate by 30%. Mannitol and glycine retain the flow rate of the no excipient buffer. When I get into higher protein concentrations, I don't want to worry about the impact of my excipient on the flow rate. So this is information I got from Big Tuna. If I had exchanged by dialysis, I would have no insight into this. If I'd done this by centrifugation, I probably wouldn't have stopped to note these volumes and calculate the flow rate. Here, Big Tuna gives me this extra information as a bonus for doing the buffer exchange that I was going to do anyway. If we take the TM data and overlay it with Big Tuna's flow rate plot, like this chart here, we can see the best combination easily. In summary, mannitol, glycine, and sucrose can improve thermal stability when compared with a 10 millimolar histidine base buffer with no excipient. Those TM values are represented by the first 4 yellow dots on the chart. Glycine, followed by mannitol, have consistent flow rates with the no excipient buffer, with glycine as excipient combining the highest flow rate with the highest TM. So I hope I've demonstrated to you that this is how Big Tuna, with some help from Uncle, can streamline and miniaturize formulation screening development and add an extra piece of developability information earlier in the formulation screening process. So in many stages of biologics development and protein characterization, Big Tuna should be able to free you from the chore of buffer exchange. I hope today I've given you an idea about the flexibility and versatility of the Big Tuna platform and shown how automating buffer exchange can allow you to do buffer exchange faster with less manual intervention, while also providing additional insight into your exchange process. Thank you for listening to the webinar today. If you have further questions about Big Tuna, please feel free to go to the website, unchainedlabs.com. There's other additional webinars and application notes for Big Tuna on the product page, or email me directly at joe.barco@unchainedlabs.com. We do have time for some Q&A, so I'll turn it back over to Adrian to moderate that. Thank you.
Thanks, Joe. Thanks for a great overview of how Big Tuna can speed up buffer exchange and sample prep. Got some good questions coming in. And just a reminder to everybody, you can still ask questions by clicking on the Q&A on the bar on the top or the bottom of the screen. So Joe, first question. Do you have to use the whole plate on Big Tuna, or can you just use some wells? And can you reuse the plate?
Yeah, you do not have to use all the wells at once. So when you're setting up the run, you can just pick some wells. You can use the rest of the plate later. Don't recommend using the same wells over again because there's a risk of damaging from pipetting the sample out or cross-contamination of samples from run to run.
Okay. Another question. My protein is sensitive to shaking. Do I have to shake?
You don't have to, but it definitely helps. So I mean, we've seen a lot of times that you can actually shake some of the time too. So you can shake the entire time during the pressurization cycle, or you can only shake for part of it, or not at all. We know not shaking at all really slows down the exchange process a lot. I do want to point out that depending on the application, like say, for example, if you're doing formulation screening, you're looking at a lot of different conditions at once. So probably if you know that a formulation is causing aggregation or a problem relative to everything else, like that's as good of a rule out option as any. I also think that in comparison to other, a lot of kind of our experience with protein work, maybe in graduate school, where we're looking at things that are like just a single formulation or a construct that's not optimized, we kind of have in our head that proteins are super sensitive. And if you look at them funny, sometimes they crash out or problems. But then at the same time, we'll put 2,000 times the force of G on it when we're in a centrifuge and not worry twice about it. So from my perspective, the stress that Big Tuna might add by orbital mixing isn't that much different than those things.
Okay, thanks. Just a reminder to everybody, if you want to ask a question, just click on the Q&A at the top or the bottom bar and type your question in and we'll try and get to them. Okay, another question, Joe. Have you looked at different molecular weight cutoffs exchanging faster?
Yeah, we have, and at least in our hands, it's not made a difference in terms of flow rate. So I think we've seen this in say centrifugal filters where it does make a difference. In Big Tuna plates and on filter, it doesn't seem to make a difference, and I don't know if that's because it's orbital mixing at the same time. The protein's not concentrating at the membrane, and that's why. But it doesn't seem in our testing to have an effect on flow rate or the overall experiment.
Okay, cool. Can Big Tuna be used for biotinylation or labeling cleanup or for ADC conjugation?
Yes. So we have an existing customer that does ADC coupling with this on a customized platform with the same kind of big buffer exchange pressurization box. So we have that, a customer doing that already. And then we have a proof of concept work going on in a lab where we're working on biosimulation work, and hopefully we'll have that data finished in a month or so.
Okay. Another question. When you use a plate, does the whole plate have the same molecular weight cutoff?
Yes. Yeah. So the whole plate, the whole bottom of the plate is that same RC membrane with the same cutoff.
Okay. Another question about related to time. So can we time the start of the buffer exchange, and will we get the waiting times needed for the process?
I'm sorry, could you repeat the question?
Sure. Is the buffer exchange process timed, and do you get the time of how long it will take at the beginning of the process?
Oh, okay. So yes, so when it starts, it will go through a process, kind of a ramp up process where it'll do a short exchange pressurization or short exchange time. And what that is doing is Big Tuna is calibrating on the fly as to what it looks like, what that well is going to look like. So you enter the concentration of the protein, but it doesn't really know how it's going to flow in that buffer. So it does a short pressurization time, figures out the flow rate by measuring the volume after a few minutes, and goes back and pressurizes some more. And so throughout that process, it's calibrating as to how are your samples going to run. That's all walk away. You've already walked away from it at that point. But then from there, it figures out that cycle time and then uses that throughout. So then that first pressurization cycle is done. It figures out how many cycles are left and then gives an approximate time for when it expects to complete.
Okay. See if we get any other questions. Seems to be it. So thanks for answering the questions, Joe. Thanks for the presentation today. Just wanted to take the opportunity to thank all of you that joined us live today. And just with many of us working from home, it's a great time to explore new ideas, new solutions to problems. So if you'd like to get a deeper understanding or have a conversation about Big Tuna and how it might fit into your workflow, please don't hesitate to get in touch with us. Our team would love to connect with you via a Zoom meeting. So thanks again for attending our webinar today, and hope you have a great rest of the day and stay safe. Thanks a lot.
Thank you.
Bye, everyone.